Good morning. Today we will discuss about pulse modulation. In pulse modulation, let us discuss about digital line codes. The introduction of digital line codes. So here communication system, it can be classified into analog and digital systems. Analog and digital systems. In the case of analog system, the electrical waveform which carries the information is replica of information signal, which is exact the same copy of the information signal, which is nothing but the original signal. So the electrical waveform follows variation in sound pressure. In the case of digital systems, the electrical waveforms are coded representations of original information. Coded representations of original information. Symbols, units, bits, and words. So the word symbol, which refers to a mark or token that represents something else. So letters of alphabets are the symbols representing spoken sounds, and numerals are the symbols representing the quantity. A binary alphabet has only two symbols. Already we know 0 and 1, which is known as bits. Also we can call it as bit, which is a unit of information. So information in bits generally defined as I equals to log base to 1 by p sym, p suffix sym. So this can be written as minus log base to p sym, p suffix sym. So here the p suffix sym or p symbol, so which is the probability of selecting symbol, probability of selecting symbol. So the information contained in the symbol is I equals to minus log base to 1 by 128. So here the previous we have seen the 1 by p probability of selection, the symbol, so which is 1 by 128. So here 1 by 120, it is the probability. So here by solving this minus log base to 1 by 128, this is 7. So 7 bits per character. For random character selection, probability of binary 1 which is occurring is equal to that of the 0 occurring, which in turn equal to half. Hence, I equals to minus log base to 1 by 2, which is equals to, so this value, which is 1 bit per minute. So a source of m characters can be represented by a binary output of m bits per character, where capital M equals to 2 power small m. Once the symbols are modulated into waveform, each symbol occupies a given time, which is known as symbol period. It is represented as T symbol. So in terms of symbol period, the symbol rate is defined as symbol rate RSYM, which is equals to 1 by TSYM. So this is the symbol period. This is the symbol rate. R represents rate, T represents here period. So symbol rate, and this is the symbol period. So the bit rate, which is represent R suffix B, which is in terms of bit period T suffix B. Here TB is the bit period, which is given as RB equals to R suffix B equals to 1 by T suffix B. So in the process of converting m bits into an capital M symbol, the relationship between symbol duration and bit duration is given as T symbol equals to m into TB. T suffix b. So thus it follows that the transmission rate, which are related by R symbol, symbol rate equals to bit rate by small n. So here TB, it is the bit period. So if pulse width is tau, then the condition is tau less than or equals to T symbol, and that the pulses be equispaced on time axis by the amount T symbol. Next one, functional notation for pulses. The shape of the pulse representing a symbol is function of time and represented as P of t. Shape of the pulse, which is representing a symbol, it is a function of time and represented as P of t. The rectangular pulses are encountered, so frequently in communications theory, P of t equals to, which is similar to rectangular small t by t. So RECT, t by t, tau. So this represents rectangular pulse of duration tau centered at t equals to 0. So P of t can be defined as P of t equals to 0, 1, 0, 0 for t less than minus tau by 2. 1 is for when t lies between tau by 2 and minus tau by 2. That means here t less than or equals to tau by 2, or t greater than minus t by 2, minus tau by 2. And 0 for tau by 2 is less than t. So here for these two conditions, P of t equals to 0. For this condition, we have P of t equals to 1. So if the pulse is displaced along the time axis by the amount t, then equation 1 may be written as P t minus t equals to, which is similar to rectangular t minus t by tau. Simply we have replaced this one here in the place of t, we are replaced here t minus capital T here also. So in this case, t equals to capital T, so which gives p of 0 equals to 1 and which can be written as non-return to 0 NRZ pulse, and the pulse width is equal to the symbol period. So in return to 0, here we have non-return to 0 NRZ pulse, the pulse width is equal to symbol period. And in the case of return to 0 RZ pulse width is less than the symbol period and often made equal to 1/2 the symbol period. Next one, line codes and waveforms. So the line codes refers to the way in which the symbols are encoded by means of the pulses. Here line code, which refers the symbols are encoded by the means of pulses. The simplest way of encoding, it would be have each symbol represented by a non-return to 0 rectangular pulse. So this is called level encoding because the symbol is encoded into pulse level. Line waveform consists of a series of rectangular pulses of duration t symbol, there being m levels for a code with m symbols. So the line waveform, which is represented v of t equals to sigma k equals to minus infinity to plus infinity. Here I told, here the series waveform consists of series of rectangular pulses of duration t symbol. So here sigma k equals to minus infinity to plus infinity ak rectangular t minus k t symbol by t symbol, period symbol. So here ak, it is the amplitude of kth symbol which is centered at the time t symbol, period symbol. So here this is the unipolar non-return to 0 code, and here this is binary 1 and 0. So this is here amplitude 2a and it is 0, and here a 2a. So here this is bit period from here to here. This is representing 1 and this is representing 0 here down. So this is 1 bit period and this is 1 bit period. So like this here we have, and this is part of the random binary stream. And here if you see, here it is 2a, and this is for 1, 0 here again 0, 0 voltage, 1 at 2a, again 1 at 2a, 0 again it comes to 0 voltage. So again 1, 0, 0, again 1 at 2a. So this is time, bit time. And here this is the alternate current waveform, and here 0 minus a plus a, sorry, minus a plus a, and here for 1 plus a, and for 0 it is minus, here minus a, 1 again 1, for 0 here again 1, 0, 0, 1. So this is the alternative current waveform. Next topic, alternate mark inversion, AMI line code. So in the AMI code, binary zeros are coded as 0 voltage, binary ones are coded as alternatively plus A and minus A, which gives rise to the name alternate mark inversion. Here we are considering zeros as 0 voltage, which is considered as space, and binary 1, if you see, alternative coding plus A and minus A. So that because of this coded alternatively plus A and minus A, it gives rise to the name alternate mark inversion code, AMI code. This is also known as bipolar code. So for example, this is the pulse 101110001. And here for 1 it is plus A, for 0 0 voltage, and for 1 again minus A, again plus 1 plus A, and for 1 minus A, 0 0 0, and here we have considered minus A, so plus A, alternative. So plus A minus A, plus A minus A, plus A. So alternative mark inversion because we are considering plus a and minus a as alternatively. So this is the AMI sequence for 10111001. So alternating binary symbol between one positive and negative voltages of equal magnitude means that the DC level remains at 0 even where long strings of binary ones occur. That is, DC Wander problem is eliminated. So this is widely used for the digital communication and it is less efficient in the coding sense. Coding symbols are not independent of one another. So power spectrum density is more difficult to derive, but the results of spectrum analysis yield the following expression for the power spectrum density. This is the expression for the power spectrum density. G of f equals to bit rate TB into A sine f TB sine pi f TB whole square. So the nulls occurring at 1 by TB rather than 2 by TB in Manchester code. Spectrum width is half that of the Manchester code. So hence AMI codes are here. A digital communications technique to maintain system synchronization. So this is the Manchester one. This is AMI. Next one, high density bipolar HDBN line codes. High density bipolar codes are so called because they contain higher density of marks, binary ones, than normal bipolar AMI code. So if the sequence have more than n zeros are encoding using HDB rules, here S will be used to indicate a space for the binary 0 and P and N are for positive pulse and for negative pulse which are encoding for the binary 1. So 0 for the space, P and N are positive and negative pulse for binary 1s. Most popular HTTP3 code in which 000, if you have the fourth 0 sequence, it is encoded by the sequence SSSX. That means here we will consider 3 spaces here, X and YSSX. So X mark that violates the AMI code, Y mark does not violate the AMI code. And equation for the power spectra for HTTP3 is difficult to derive the encoding bits which are not independent and on average there will be more marks than the spaces. So if you see it here, this is the AMI code and here this is for HTTP3 code and this is alternate mark inversion and this is the original message 101000001 0000110. So here, if you see for 1, this is the original message, and here this is AMI. If we consider 1 positive and 0 space, and for 1 negative, and for zeros 1, 1, 2, 3, 4, 5 zeros. We have 1, 2, 3, 4, 5 spaces here. For 1 here we have considered negative, so here positive. And again we have zeros. And here for 1, here it is positive, so negative 1. And here P positive. Here it is negative means it is positive, then space. So this is how we can express in AMI. And if we consider in HDB3, so here let us see for 1, positive P for 1, S for space 0, and here N for positive. And here if we consider here zeros, S, if we have 4 sequence, we have S, 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 and 1. We will consider here n. So again, if we have again 4 sequence zeros means we will consider SSSP here, and here we have let us see. And here we have, if we have a 4 0 sequence, it is encoded by sequence SSSX and YSSX. So based on this, we will see here for 4 zeros, we will consider 3S and N. So here also we have 4 zeros. So here we will consider SSS and T. So based on this, we will draw this one. For P, it is upper, positive A. For S, it is space. For N, it is down, negative. For S, we have 3S. So 1, 2, 3. And for this 0, we will consider N. Again, space. For P, it is upper and 3 spaces, 1, 2, 3. Then again, we'll have P, N, P, S. So like this, we will see this HDB3 code. Next one, M-array encoding. So with M-array encoding, symbol rate is less than bit rate. So that means symbol rate R symbol, which is equals to bit rate by M. So here M is number of bits contained in a symbol and capital M equals to 2 power n. So as with binary transmission, polar transmission for M array waveforms is more efficient in terms of power when the levels are centered on 0. For a separation of 2A between levels, the M array waveform requires that here this is the condition for M odd, for M even. So for M odd, we will take AK equals to 0 plus or minus 2A plus or minus 4A plus so on plus or minus capital M minus 1 into A. For M even, we will consider plus or minus A plus or minus 3A plus or minus 5A plus so on plus or minus M minus 1 into A. So let us see. For the digital ratio system, we have 2 power M minus 1. So here M equals to 8. Why it is 8 means here 1, 2, 3, 4, 5, 6, 7, 8. Here we have considered M equals to 8. So 8 minus 1 equals to M minus 1 equals to 7. And once look at here. So this is 1, 2, 3, 4, 5, 6, 7, 8. So for M equals to even. For M is even. So let us see. For M is even, we have to take the condition plus or minus A plus or minus 3A plus or minus 5A plus or minus M minus 1 into A. So we have to consider this one for M is even. We have considered for M is even. And here, once look at here, we have 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1. And here we will find out the values. 1, 1, 0 is 6, 0, 1, 1 is 3, 1, 0, 0 is 4, 0, 0, 0 is 0, 1, 0, 1 is 5, 1, 1, 1 is 7, 0, 1, 0 is 2, 0, 0, 1 is 1. So how we have to calculate? So like this. So for 1, 1, 0, we have to calculate 0 into 2 power 0. So 2 power 0 is 1. 1 into 0 again 0. So value is 0. 1 into 2 power 1. So it is 2. 1 into 2 square 4. So total we have 4 plus 2 6. So like this 110 means value is 6. So 1106 like this we have find out the values. And here if you consider total M here we have M is 8. So 8 minus 1 we have 7. Why? Because here if we consider M minus 1 into A up to M minus 1 into A for M is even. So M 8 we have. So M minus 1 into M is 7A. So 7A. So based on that we have 7A. We have to consider the values plus or minus A to 7A plus or minus 7A for M even. So based on that, plus or minus A to plus or minus 7A. So here these values are 6, 3, 4, 0, 5, 7, 2, 1. And how we have to arrange it is 0, it is the smallest value. So small, what is the smallest? We have minus 7A. So next one, minus 5A is least, 2, minus 3A, 3, minus A. Next one, uh, plus A, 4 plus A, 5 it is 3A. Next we have 6, 5A, 7 it is 7A. Like that we have to arrange from smallest to highest value. So 0, 1, 2, 3, 4, 5, 6, 7. We have these values. So we have to arrange from smallest to highest value. So minus 7A, For 1 it is minus 5a, for 2 it is minus 3a, for 3 it is minus a, for 4 it is plus a, 5 it is plus 3a, 6 it is plus 5a, 7 it is 7a. So like this we have to arrange. So based on these values based on this arrangement we have to draw the graph. So here for 6 it is 5a, so we have to draw 5a, 3 here minus a, so 5a minus a, again for 4a, for 0 we have minus 7a, for 5 3a, for 7 it is 7a, for 2 it is minus 3a, for 1 it is minus 5a. So like this we have to m array encoding with m equals to 8 levels. Like this we have to draw. So the M array system requires 1 by m of the bandwidth required for the binary system. So alternatively, for a given bandwidth, M array system can transmit information at m times the bit rate of the binary system. So advantage of M array is that it allows the information at fixed bit rate to be transmitted over a smaller bandwidth system compared to the binary transmission. So differential PCM or DPCM. So here DPCM, it is a signal encoder which uses the baseline of pulse code modulation but adds some functionalities based on prediction of samples of the signal. So if the input is a continuous time analog signal, it needs to be sampled first so that the discrete time signal, that is the input to DPCM. So here I will explain this one by seeing the graph. So this is also we will show. So here this is the DCPM transmitter, and here uh, here these are the samples. These are the samples, input samples. So here these are the samples which we have to make. The sample will sample the input. Uh, Here the sample this output here we will see. Here this is the predictor, and from here uh, here first we have to consider all the samples. So we have to take the output from the predictor. We have to take the output from the predictor, and we have to take the samples, and we have to difference these two so that the differential PAM will send to this quantizer, and the input will get to the predictor from this output of the quantizer. We will get the input to the predictor from the output of the quantizer, and here so that we have to send these output of the quantizer to the binary encoder, so that finally we will obtain the line waveform output for the TPCM. So like this we have to transmit. So these are the samples. We have to take the output of this predictor, difference of this output of the predictor and these samples, so that we'll obtain the differential PAM. So we have to send to quantizer, and the input to the predictor will obtain from the output of the quantizer, so that we will send the this differential PAM to the binary encoder, so that we will obtain the line waveform output for the DCM. This is the DPCM transmitter, and this is the DPCM receiver. And here line waveform input for the DPCM. So we will send to the regenerator. So it will send to the decoder, so that the output of the predictor and differential PAM. So here the combinedly we will send to the we will obtain this output and this differential PAM. So these two by we have to send to this reconstruction filter, so that we will obtain the analog output. So this is the DPCM receiver. So advantages: bandwidth requirement of DPCM is less compared to the PCM. Quantization error is reduced. Sample values are also reduced compared to the PCM. Thank you.